Okay, we're going to start the next session. So this is Tahoe, robust distributed secure file system, presented by Brian Warner. Brian Warner is a programmer, electronics hobbyist in San Francisco. He's also the primary author of BuildBot. Also author of Foolscap. However, as he just mentioned to me a second ago, Tahoe is what is taking up all of his time right now. So, without further ado, Brian.
Alright, so let me tell you about my day project for the last year and a half. I'm eating up all my fun project time. This is a fun project. So, all my data Tahoe is a robust, secure remote file system. I'll talk about what each of those pieces actually means in a second. The Tahoe project is fully open source. It's distributable into the GPL in addition to a couple of more local licenses than that. It implements a distributed file system, remote file system. How many people were in Jonathan's presentation for Mozy just a little bit ago? And how many people weren't? Okay, cool. So there's a lot of overlap here. If I don't cover the salient differences between them, ask me during the Q&A, and I'll try to cover that more specifically. I didn't get to see his presentation, didn't know much about price tracking before doing this, so you'll see a lot of overlap. This project is sponsored by allmydata.com, my employer. We are using it at work for the backend server for our consumer backup service. We have a service we have open a month. You get some online storage to back up your home files, specifically aimed at home users, mom and dad, and shop. And we're using this as a backend for it. This is all written in Python, obviously. It makes heavy use of Twisted for application services, event loop, all of the inter-process communications using Foolscap. We've got a build-out running on it. Like all of my home projects are getting used in this work. You can find complete details at allmydata.org. I highly encourage you to go check out the track, check out the build mods, grab a copy of the source, go and play with this. There's also a copy of the related paper that I wrote in this available there. And we just released Omega yesterday, and we're in the process of making the allmydata.com commercial release today or Monday or whatever. So, what is a file system? Well, we all kind of know that. It's a place where you store data. It helps you organize files, things that are important to you, pictures, notifications, stuff like that. It's a bunch of files and directories. It sits on a disk somewhere. There are things like exe3 and RESTful and CFS, HFS Plus, that know how to actually organize this and do it in some useful fashion. Most of the time, this sits on a local disk, which is sitting there inside your house, where you can get to everything. That's all great. Why a remote file system is the same kind of thing, but it's somewhere else in the world, and you have to get to it through the internet. There are a couple of different protocols that have been established for this. Webdev, a lot more human-oriented, not so machine-accessible things, like a web server where you upload files, or a page-sprint. There are plenty of services that you can put files to get back and out. So, think of a file system as kind of a general purpose thing, not specifically the exe3 thing that you access and control. Now, why might the remote file system possibly be better than a local one? Well, one is just accessibility. You're out traveling somewhere, you can get to it from various places around the world. Whereas your system at home doesn't tend to be available to you when you're out there on the road somewhere. It's an unfortunate fact that the way modern networks are set up, there are all of these roadblocks put in place that prevent you on the road from getting to a server running inside your home, even if your home computer is perfectly capable of running that service on its own. There are NAT boxes, there are firewalls, IP addresses change all the time, make it hard to reconnect to that same server, and sometimes ISPs are just hostile. They don't want you running the server there, they want you to be more consumer. In addition to that, the data that's sitting there at home, sometimes bad things happen. There are machine failures. The home is kind of not so great environment for computers when you think about it. There's lots of dirt there. There's fire, blood. If your reporter will force you off the building your computer, and then suddenly it doesn't work anymore. So bad things can happen when the data is at home. And there's a big problem there because these are correlated failures. You've lost your house and you've lost your pictures. That just really sucks. So the remote system gives you decorrelated failures. My house burned down, but at least I still have my vacation photos. This makes people a little bit happier. Remote data is safer, but bad things still happen. Data sitting in a colo facility somewhere is still vulnerable to natural disasters. It's also vulnerable to fiber cuts or to internet availability problems, routing problems. There are slightly fewer FOIA rules on drop of mail to the server in a colo facility, but you never know. kids are growing up fast these days. So redundancy is what we want to use to try and get this kind of robustness out of it. If data is not available in one server, there should be some mechanism of failing over to a different one, so that you would have to have meteor strikes or something to take out all of your photos and piece of data. In addition, secrecy is really valuable. Some data is more valuable when nobody else knows it. And there are plenty of reasons why you might not want somebody to see your contact with your appointment book or your phone number or whatever. Keeping local data secret is relatively easy. If you keep this inside the house on a computer, well, okay, it's not plugged into the internet. But if you have doors, you have locks, an observer, an eavesdropper who's trying to peer into this data can't actually see it because it's physically accessible. This is the reason why we have firewalls. It is a sometimes useful feature of that boxes as well. It's a little bit unfortunate that we can't seem to build applications or operating systems that we trust well enough to not give out our secret data for the output. But that's the problem. That's probably the main problem. Keeping remote data secret is a little bit harder because you don't really know quite where it is. To start with, the person who's holding this data for you gets to see it. And what reason do you have to believe they're not going to look at it or take advantage of it or sell it somewhere? For a lot of systems that don't try to do any kind of encryption, they just keep the thing in plain text out there, all you have is their word for it. You're trusting some privacy policy that is going to change when their business needs change, or somebody gets subpoenaed, or somebody gets pressured by a big or whatever. Then you have all of the other potential eavesdroppers to worry about. People that can watch the data moving to and from the server system. People that can somehow break into that remote system. So now this eavesdropper is much happier about the situation because there are a lot more opportunities to do this. So this is a situation where encryption comes together, where you're taking a fairly small piece of data, secret data, the key, everybody uses AES, and it renders the data unusable unless you actually have that key. What this does is to transform the problem into keeping the key secret instead of keeping the whole piece of data secret. And keys are really small. So they're small enough you might be able to you can carry them around with you, flash drive, or you may be able to just remember them if it's something derived from password of some sort. So this further frustrates the observers that it's so encryption is good to help provide the things. Integrity is also valuable. Most data is much more valuable if we know it hasn't been changed. Sometimes it's just a nuisance, sometimes it damages a file in some fashion, or sometimes it might come with severe consequences. We're depending upon computers to keep track of more and more things. We're entrusting more of our memories, more of our personal information into machines, and we have this implicit assumption that it's not going to change it, or somebody won't be able to change it for us. So this is where cryptographic hashes come from. I assume everybody's familiar with SHA-256 hashes. It's an compression code that squishes a big piece of data down into a small one in such a way that you can't take some other piece of data and make it look like that same hash. So if I remember that the hash of this particular document is a string, it's whatever, then somebody else can't, as long as I remember that string, somebody else can't give me a different document because this is what it is like. So this is a way of helping us tell the difference between the real data and the fake data. So these are the goals of Tahoe. We want something that is secure, provides both confidentiality and integrity. It is robust, something that is not going to be susceptible to failures, so something that increases the overall availability and long-term reliability of the data. It's something that is remote in that it's reachable from a number of different places. I want to be able to get to my files both from home and work while I'm at home. And it's fast. It helps organize things with files and directories. So the Tahoe grid is a collection of clients and servers. The client is a program running on your computer. The storage servers are running on a bunch of other machines. We've specifically designed this system to be deployable in a couple of different use cases. The ones that are most important to us are the FriendNet and the commercial net. As hackers who want to use this for our own purposes, I've got 50, 100 gig of free space on my computer at home that I'm using. I've got a friend who's got the same. It would be really nice if I could back up my data on their machine and their data on my machine. So it's very easy to configure a Tahoe system in a FriendNet where each participant runs both the client and the server, and they all talk to each other. And then I'm pushing files from my machine off onto the other ones because that then gives me better reliability. My machine goes out as long as a couple of my friends' machines are still there, I can still get my data back. That's not to say that I trust these friends of mine to not look at the data or try and interrupt it. So we want to make sure that we have enough hashes and enough encryption in place, that the only thing I'm relying upon those remote systems is that they have a piece that they store a share for me, and they give it back to me at some point in the future when I ask for it. None of the security properties that we have depend upon the storage servers behaving in any fashion at all. All they have to do is store data. They're not asking to not gather it. What almadata.com is interested in is using this as a backend for a commercial service. So in that system, customers are paying us to store their data. They're not providing storage space on their own. It's an interesting problem to take advantage of storage space like offered there. A previous version of what this company has been doing is then to have customers pay you either with money or by providing disk space. That is a possibility within the system and in the bring that system, but we're not really focusing on it right now. It's a challenge to know whether that's going to be reliable. It's a challenge to find out what sort of access speed you're going to have to do it when it's looking around. So a commercial deployment is going to be focusing on clients at the same time servers. And all of your servers are going to be sitting in a location facility somewhere, where you have nice clean power and UPSs and a lack of really low problem. In fact, we simplify this a little bit. We have an introducer node that manages these connections. So clients only need to be configured with the location of the introducer, and the introducer tells them about all the other storage servers. If you're familiar with Foolscap at all, or Twisted Spread with the Perspective Broker, all of these connections are Foolscap. These are effectively secure remote object connections. These are methods across like storage or share with you guys. So, how does this work? When the client wants to upload a file, the very first thing they do is to decide on an encryption key. There are two different ways of doing this. You can choose one randomly, or you can hash the contents of the file to give you a key that is only available to somebody who already has the file. This has the nice property of conversion, because if you try to upload the same file twice, it'll come down to the same key. You'll notice the file is already out there in the grid, and you don't try to store it. Once you have this key, then you encrypt the data with it, and you wind up with a ciphertext. And then you subject that to erasure code, which is this really, really clever thing that John really pointed out, in which you take a file and you split it into a bunch of smaller pieces, and you only need some subset of those pieces to be able to recover the file. The nice thing about most forms, there are a lot of forms of erasure coding which is all very configurable. We're using a library that Zuko wrote called ZFEC, which is a wrapper around the Rizzo codec. This has the property that you can choose how many shares you need to take the file back, how many shares you create total, and it can create about 256 shares of using one of these. Our default encoding for Tahoe right now is very conservative. We have it set at 3 out of 10, which is effectively tripling the size of the data. What we're doing is collecting information on how reliable things are, and we need to do some more simulation work on that. But I expect we can be able to drop that down to 20 to 30% over time. Jonathan mentioned maybe doing something like that as well. So that's entirely configurable every single file to get the different sorts of code. Then once we have those shares, then we need to push them out to storage servers. We put each share on a different server. By having them on separate servers, you get mostly independent failures, and that helps you take the reliability risk. The way that we actually decide which server to push the share to is using a technique called hash-based permutation. So we actually, every file has a unique storage index, which is just a random 32-byte string. But it's derived from the hash of the encryption key, which in many cases is derived from the hash of the file. So that gets us that conversion file. The storage index is used to permute a list of storage servers. It looks random, but it's consistent. Every time you take that same list and use the same storage index, you get back to something new. So basically, this is just choosing, okay, this particular file is going to be stored there, and then there, and then there, and then there. And the reason we do this is to spread out the node. We want to make sure that there's not one set of storage servers that are getting really hammered, just because that one file happens. It's a low distribution mechanism, and it also is the intention is to control failures even further. So when it comes time to recover the file, we just run the system in reverse. We start with the storage index. We find all the storage servers that are there that have the shares that we need. We pull those down. We submit it to erasure coding in the decode mode. We get back the plain text. Then we take the encryption key that we remember, decrypt it, and get back the original So every time we upload one of these files, we wind up with two values. We wind up with shared out the server and storage grid somewhere, but we wind up with an encryption key, and we wind up with a hash of the data that's on there. We combine these into a fairly short string that we call the read capability. It's like a URI in the sense that if you know the string, you can go and get the data. It's stronger than that because it's actually a secure reference to this data. The hash that's in there means that nobody else can change the data undetected. The encryption key that's in there means that nobody else can see the plain text of this stuff unless they know it's encryption. So this read cap is everything that you need. It's necessary and sufficient to get this file back. And that makes the security properties much easier to analyze later on. If you have the read cap, you get the file. If you don't, you can't. Then these strings are short enough that you can send them around, email them to somebody who goes dry. And that allows you to rebuild a larger structure. This creates what we call an immutable slot. Once you upload this data, you can't change it anymore. The hash prevents any kind of modifications. So this is good for files. This basically gives you a big distributed hash table, or the content of adjustable grid, but you need more than this if you want to get a file system. So we've also implemented mutable slots. I won't go into the details. There's nice diagrams of it on the website. But effectively, it's using public key cryptography to associate a key with each one of these slots. There end up being two separate capabilities. There's a write cap that gives you the ability to modify the slot based on its science and data that is there. And there's a read cap, which is what lets you download it. This has the same integrity and confidentiality properties in that if you don't have a subscription key, you can't relate it. In addition, the read cap is derived from the write cap by hashes. So anybody who has a write cap can make a read cap whenever they want. So effectively, it's a read plus write cap, which is so now that we have these two primitives, how do we implement a file system? If you think about the file system in terms of directories and files, well, you might then think of it as a graph that connects directories to files via the edges. You represent all of the files through a read cap of the immutable data of that URI line. And the file names themselves are labeled on the edges of this graph. The read cap refers to a sequence of bytes. That doesn't have a name associated. It's just a sequence of bytes. It's the directory you went through to get to that piece of data, which is what calls a track byte. So then, directories are basically just a table that maps child name to capabilities like access something. We can serialize that table into a chunk of data, store that data into a mutable file, and then call that reference a directory. So directories are really just named to capability tables. We built it this way because we wanted to provide fine-grained sharing and fine-grained control over all of these different pieces. If I give you a reference, if I keep a reference to my root directory, which is the capability up here, that lets me get to everything else that I can control. However, you might give me a reference to some other directory, some other file. This is a technique for doing distributed access control. It's capabilities oriented thing as opposed to passive code or something like that. Because these directory nodes are using mutable files, and we have both read caps and write caps, we actually can store both of them in there. So we do this kind of bit of cleverness there where we encrypt the write capabilities separately, such that you have to have a write cap in the directory in order to see the write cap in the children. This lets us get transitive read-onlyness. If I give you the read cap of one of these directory nodes, you will only ever be able to get read caps of those nodes. And that lets me safely publish something. I can say, here's the directory, you can read it and see it as updates, but you can't go and change it. So this gives us fine-grained sharing, which we think is an important property, especially in the kind of friendnet scenario. You don't want to have some central service that has control over who gets to see what. You retain control over everything by withholding and revealing these capabilities to your switch. When you give that read cap out to somebody, then you wind up with a read-only reference to a subtree, so that it ends up with, you can get everything that's below there, but nothing else. The fact that this is a directed graph also important, you can't get up to some notion of parent. So the front ends that we have for this are the way that the human actually ends up using it somehow. The main one that we have right now is a RESTful HTTP interface in which you do puts and gets to specific places in order to upload data and remove data. You can do deletes to remove the edges to your graph. There are two basic consumers of this. The machine's consumer The RESTful side of it is really intended for programmers when they HTTP calls and they have access. In addition, a human can use it because we have a bunch of directory pages that give you forms with buttons to upload files and download files. It's free to prove, it's really just intended for developers and people who are hands-on. Most of the consumer-oriented things are using it under. We've also been developing a Fuse plugin to allow arbitrary applications to get access to it. These applications think they're using a local file system, they're using system calls like open, read, write, and close. And the plugin that we have accumulates those calls, builds up the file, and then does the Tahoe calls in the backend. This is a bit of a challenge. It's kind of an impedance mismatch between the traditional Tahoe file system and the Tahoe file system. So the subscriber can get out. But then applications that are actually aware of Tahoe can use this HTTP interface directly and get better performance and have more features. For instance, if the whole file is available before you try to upload it, you can tell the Tahoe node, this is a hash of the file, you check to see if this is available. You can tell the node to avoid uploading something a second time if it's already uploaded already. You can get better progress information by going through the higher level interface. There are a bunch of other features I don't have time to talk about very much. There's file checking where you want to count the remaining shares over time. Hard drives fail or the span of several years. Any individual file, the number of shares it has available will slowly decay. You want to be able to detect when that's gotten too far down and then initiate a repair, which is really just downloading the file, making more shares, and putting it back up again. A really nice feature of the graphics scheme that we use is that you don't need to be able to see the plain text in order to do the repair. So you can delegate out that to other nodes without actually giving it to the There's an upload helper that we use to allow nodes, people at home to upload a file without doing the information coding on their own. They do the encryption at home, so the ciphertext never leaves the client, but they only upload one copy of it instead of the expanded copy of the consumer. There also is a lot of work we're doing on accounts with quotas within the storage space to say, we're selling this to somebody, there's push it 20 years of space, how do people want to love that? Likewise, when I delete this, or if I leave the system and we time it out after the month, how do we know which shares to leave the server space? And then there's a lot of reliability analysis we're working on to be able to say with some level of mathematics, files will on average last for this many years because we repair at this rate to this kind of thing. That's there to not just make some economic decisions about what sort of expansion to do. So thanks. I encourage you to take a look at allmydata.org. We have the track instance up there, a lot of documentation, all the code is visible. It's pretty easy to go and download it, and it's easy to set up a node, run into it, so it has to go and talk to each other. I think we've got time for questions. Okay. So everything, I think networks, unfortunately, there's some cool stuff in here. So everything is in Python, except for there are C libraries that we're using underneath. So ZFAC is a Python binding around the C library that does erasure coding. iCryptoPP is a library that wraps around the excellent Crypto++ library. So obviously, crypto is taking place in C for speed. We're using simple JSON, which I think might have a C extension to it. Foolscap itself uses IOPSSL, so that's at the C level there. But so those are the kind of support libraries, and then we have Twisted, Revo, obviously a bunch of standard library stuff, and then all the Tahoe code on top of it. I didn't mention too much about Python because we're not doing anything tricky or super clever with it. Obviously it makes everything easier to write, and we wouldn't be as far as we are with this if we tried to any other language. But I kind of figure everybody here knows what those are. So performance-wise, it depends a lot on what sort of latency you're getting to your backend system. If you take a look at the build bot that's on the allmydata.org track, there's a section there for performance graphs, and we actually have automated performance tests. Every time we check to make a change, the build bot kicks off a script that times how long it takes to upload a bunch of files and download a bunch of stuff. What we're seeing is the machine learning image colo, something of the order of 3-4 megabytes per second on the upload side. When you're doing stuff from home, as Jonathan was pointing out earlier, small files is a problem. Big files run at line rate, however your network is. For something at home going over DSL, we'll saturate the DSL, and that will be the limiting factor. For something in colo, I think it's the latency, the number of round trips we do, is a limiting factor. But we are easily able to saturate those sorts of networking with the high performance. So the integrating with Fuse, we have a Fuse plugin that we're developing, and it mostly kind of sort of works. As I mentioned, so we have a Fuse plugin, which is really an SMB-based protocol, and we have an OS 10 Fuse plugin running. And the OS 10 Fuse is intended to be API compatible with the one. So it ought to work with Linux, but we haven't actually tried it out yet. That works reasonably well, but there's a lot of function capture going on to deal with the kind of impedance mismatch, and deal with the fact that a lot of applications don't like having their write calls work really fast, but close calls take a long period of time. We've seen some Windows applications that enforce their own timeout on that. And if close takes more than 30 seconds, then they give up and they try it again. So the current version is immutable data files and is overwrite. So basically, you upload the data here, there's a reference to it to the directory. You upload the new version, now you have a reference to the new one, this is now a version. We don't have code in place yet, we don't track that stuff down. But what we do have is each one of these shares around the back end has a lease associated with it that says, I care about this or I care about this or I don't. And we're working on building that up through reference catalog on the back end and drop those stuff. It's kind of tricky to figure out when to schedule that stuff because there are applications where why bother deleting stuff? Like, can we figure out the rate at which people are modifying things, deleting files, and does it make sense for us to put engineering time into making sure we get that stuff right, or can we buy new hard drives fast enough to make that issue? It's kind of a tricky call, but so that's why we've scheduled that thing. We're working on that now, but we kind of scheduled it out. We do not at the moment, but we have plans to, so the mutable file implementation we have at the moment is fairly primitive. We've intentionally limited it to 1 megabyte. So it's good for directories up to 10,000 entries or something, but it's not a general purpose mutable file construct yet. We have plans in place for a more general one that will include versioning information in it. So in fact, every mutable file will have a version tree that says this version derives from this one, derived from this one, kind of like a distributed revision control system. In that one, we can then build a directory node on top of that, where if you have some sort of revision identifier, like you do with Mercurial or BZR, where you say, here's the hash of that particular revision identifier, then you could ask the system, show me the contents of this directory for this particular tag. We can add metadata into there, like again, most of the revision control systems do, to ask that same question based on the timestamp. So, especially as a backup application, it's really interesting to us as a company to be able to say, show me this directory as it was a month ago. Very much like the way that Time Machine does it on that. I will be around later on. If you guys are interested, you can do a log on this stuff and we can talk more about it. Find me afterwards. Thank you all very much.